All right, so now we can talk about Gaussian quadrature and to show in what precise sense it is optimal. So let me sort of make the following claim that no quadrature formula with n+1 nodes, right, is exact for all polynomials P in P m of x, where m is greater than or equal to 2n plus 2. Okay, so what we're going to show again is that that Gaussian quadrature is exact with n+1 nodes for polynomials up to degree 2n plus 1. All right, and that no quadrature rule is that with the same number of nodes can be exact for all polynomials of degree 2n plus 2 or higher. Okay, and the way you do this obviously is you construct a counterexample. So let's show that. So we're going to construct a counterexample. We're going to construct a polynomial of degree 2n plus 2 for which, again, no quadrature rule with 2n plus 1 points is going to be exact for. So I consider the following. So I'm going to consider p of x, right, which is given by the product from I equals to 0 to n of x minus xi squared, right? So there are n+1 nodes corresponding to x0 to xn, okay? And I'm going to have a polynomial which is x minus xi squared, and then I take the product of these things. So, and this obviously is greater than or equal to 0, right, over the entire interval. And in fact, it's strictly larger than 0, right, away from the nodes, okay? So, and sort of, so strictly greater than 0, except at a finite set of points. Okay. All right, and obviously this is in p2n plus 2 of x. All right, and you can check, again, it's easy to convince yourself that integral from a to b of p of x dx is strictly greater than 0. Okay, but let's think about what the corresponding quadrature rule is, right? The corresponding quadrature rule is that you have ai, some unknown coefficients, times pxi, sum from I equals to 0 to n. Okay, but p at xi, right, by construction is 0. Okay, so this is just the sum from I equals to 0 to n of ai times 0, which is 0. Okay, so we've arrived at a contradiction. Well, not really a contradiction, right? But we've sort of demonstrated that here there's a polynomial of degree 2n plus 2 whose exact integral is greater than 0, but whose quadrature approximation is equal to 0. So clearly, right, whatever quadrature rule you have, so long as it's of this form of some linear combination of the function values at n+1 nodes, right, that can't possibly give you the right answer. Okay, so the quadrature rule is not exact for all p, which is in p2n plus 2 of x. All right, and of course it's like any space of high degree polynomials will also contain, it's like this, and so you can use the same counterexample. Okay, so that's basically the first observation, right? It tells you that if you have n+1 nodes, the best you could hope for in terms of exactness for all polynomials in up to a certain degree is up to 2n plus 1. Okay. Okay. So so now let me say something about you know, it's like the construction we had talked about earlier, which is that I'm going to have a Gaussian quadrature rule where the quadrature points come from roots of some orthogonal polynomial, and then the quadrature weights come from this Newton-Cotes type construction. Okay, so let me state the theorem. And then at the same time as stating the theorem, I'm also essentially going to state the Gaussian quadrature formula. So let x0 to xn be zeros, right, of the nth plus first orthogonal polynomial. Right, relative to a weight function let's call it W. Okay, so what's going to happen basically is that you can look at Gaussian quadrature rules for weighted integrals instead of just regular integrals. And so the weighted integrals involve this weight function W, which is non-negative basically, right? Then if you don't want to worry about that, you should just think of W being identically 1. It's like in the formulas, but it applies, the construction applies for this more general construction. Okay, so then the quadrature formula where the integral from -1 to 1 of f of x w of x dx is approximated by the sum from I equals 0 to n of ai f of xi, where ai are these Newton-Cotes weights, right? So it's integral from -1 to 1 of w times this product from j equals 0 to n j not equal to I of x minus xj over xi minus xj. So this is just a Lagrange polynomial, but then appropriately weighted by this weighting function. Okay, all right. So that's sort of the natural generalization. It's like of the Newton-Cotes formula to weighted integrals. Okay, but again, if you don't want to worry about weights, you just think of W as being identically 1. Okay, so this formula, right, where the xi's are roots of the n plus first orthogonal polynomial, and the weights are sort of the obvious generalization of the Newton-Cotes weights, right? This is exact on polynomials of degree 2n plus 1. Okay, so let's try to prove this. Okay, so I want to start with a candidate function. So let f be in this space of polynomials up to degree 2n plus 1. Okay, okay, so this n plus first orthogonal polynomial is going to be a polynomial of degree n. Sorry, of degree n plus 1, right? So let p be a polynomial of degree n plus 1, right? With the property that p is orthogonal to polynomials up to degree n in x. Okay, so what that basically means is that you know, the inner product between 1 and p, x and p, all the way up to x to the n and p is equal to 0. Okay, where the inner product is the weighted inner product now, right? So if you have f and g, right, this is the integral from -1 to 1 of f of x, g of x, w of x dx. Okay, so there's a weight here. Okay, anyway, so that's the orthogonal polynomial. Okay, that has so this polynomial degree n plus 1. Okay, so I can write f, I can essentially divide f by p, or I can write f as q times p plus r, right, where q and where more importantly it's like r has the degree of R is less than or equal to n, right? Where the degree of R is less than or equal to n. Okay. All right. So so there's this p, which is an orthogonal polynomial. There's sort of the quotient, and there's a remainder term. Okay. And you can always do this in such a way that the remainder is a polynomial degree less than or equal to n. And the same is true of q as well, right? The degree of q is also less than or equal to n. Okay. All right. All right. So f is, let's just write it down. F is polynomial degree 2n plus 1 at most. This is a polynomial of degree n. This is a polynomial of degree plus 1 at most. Well, actually, it's not at most. It actually is a polynomial degree n, right? And then this is a polynomial of degree n at most. Okay, all right. So with that in mind, let's see what we need to do. Okay, so the idea is really simple, right? So I've written f in this way, and I'm going to evaluate both the exact integral as well as the quadrature approximation and see what happens. Okay, so the integral from -1 to 1 of f of x dx, right, is equal to this thing. So it's integral from -1 to 1 of q of x. I should have the weights there, I'm sorry. Okay, so f of x wx dx is equal to the integral from -1 to 1 of q of x p of x plus r of x wx dx. Okay, so this is equal to the inner product between q of x and p of x, right? That's the first term, plus the integral from -1 to 1 of r of x w of x dx. Okay. All right, so this term vanishes because q of x is polynomial up to degree n of x. And then by construction, p is orthogonal to Pn of x, so all these things vanish. So this vanishes by orthogonality. And what you're left with is this thing here. All right. So let's see what happens when you have the quadrature rule. Okay, so you have the sum from I equals to 0 to n of this quadrature weight, right, which is integral from -1 to 1 of w, the product from j equals to 0 of n j not equal to I, x minus xj, xi minus xj dx. Right, so that's the weight times f at xi. Okay, so this is equal, so I'm just going to call this bi for now. All right, so sum from I equals to 0 to n of bi. Now f gets replaced again with qp plus r, right? So q of xi, p of xi plus r of xi. Okay, but what happens is that the xi's are the roots of the orthogonal polynomial, so these things vanish, right? Xi's are roots of p. So you're just left with now the sum from I equals to 0 to n of bi r xi. Okay, but the bi's are the Newton-Cotes weights, right? Okay, and you know that the Newton-Cotes weights are exact, and the formula is exact for polynomials up to degree n. Okay, and R of x is a polynomial of degree at most n. Okay, so this thing here is equal to this integral. So those things are equal. All right, and again, it's like you know, the way you show equality, if you really wanted to, is that you can replace R of x by its polynomial interpolant on n+1 nodes, right? And that's going to be exact because R is a polynomial of only degree n, right? And when you do that when you use that Lagrange interpolating polynomial expression and you exactly evaluate this, you get this. I should say that there's a weight flying around somewhere. Yeah, the weight is captured in here, right? Okay, so the W shows up in the weight here. Okay, so those two things are equal to each other. Okay, so that proves what you need, right? That again, the exact integral for polynomials up to degree 2n+1 agree with this, you know, it's like with the quadrature approximation. And here it's like we've used two properties, it's like of the xi's. The first of which is that, you know, it's like the xi's are the roots of this polynomial p. And the second of which is that that polynomial p is orthogonal to all polynomials of degree less than or equal to n. Okay, so these two things together are necessary to cancel out the contributions associated with these QP terms, so that what is left over is just this remainder term, which is a polynomial of degree less than or equal to n. Okay, and with that, it's like you can then prove that you get the method you want. So I should say that more generally speaking, you could consider polynomials of lower orthogonality, so which is to say that they're not orthogonal to all of the polynomials of degree less than or equal to n. And if you do that, it's like the same kind of argument holds. It's like, but then you won't have, it won't be true that the method is exact all the way up to polynomials of degree less than or equal to 2n+1. But every time it's like there's an additional degree of orthogonality, so to speak, right? You get one additional degree of precision that's like in your algorithm. So say P is only orthogonal to the constants, right? Then instead of the algorithm, the Newton-Cotes formula being exact for polynomials up to degree n, it will be exact for up to polynomials of degree n+1. Right, so the same argument applies. It's like with an appropriate change of this orthogonality property and what the degrees, maximum degrees are. Okay, but everything else, the basic idea sort of holds. Okay, anyhow, so that's sort of you know, the basic sort of proof. It's like of how you can get this high degree of precision in Gaussian quadrature. And again, you see the two important properties. It's like of the nodes, one of it being the roots of this polynomial, and the second of which that polynomial in question is actually orthogonal. Okay, so I'll stop here.